Everybody say hi, Alyssa.
Hi,
Alyssa. So, sorry you're not with us. Our goal for today is to make a little more progress on our project. After that, we're going to review work energy. And in particular, as we talk about work energy, I am going to, cover number 12, question number 12, which I didn't really have time to do a video on yesterday.
Can you go over number 7?
Yeah, I could take a look at number 7. When you post about a problem, give me the actual problem, because I don't always have my book with me. And then after we do that, I want, if we have some time, I want to begin talking about conservation of energy, which is where our approach with work and energy is going to really pay off in terms of giving us simple ways to solve hard problems. So our goal is going to be to have simple ways to solve hard problems, and specifically problems that ask us to find speeds. And Daniel, I'm going to pitch my review at you since you've not been with us, so let me know if there are any questions that come up. Okay? So as far as the project goes, last night I asked you guys to take a look at the Vmax situation and to come up with a free body diagram and components. And did I ask you to apply Newton to it?
Yeah.
I think so. Okay. So what does your free body diagram look like? Which way are my forces pointing? Yes.
Have mg going straight down,
Yeah.
as well as friction sine theta going straight down.
Ah, okay. Which way is friction pointing, generally speaking?
In this, so which way is the rim pointing?
Every other way like this.
Okay, so then friction would be going towards the middle of
Yeah.
the ramps because the car is trying to go off.
Uh-huh.
So do you want friction broken down or no?
Yes, let's go ahead and do that. So friction then has components. We can scratch this out and replace it with its components. And this is F sine theta, you said?
Yes.
And this would be, therefore, F cosine theta. And that is correct. Yep.
Actually, I had that guy. But, and then Fn cosine theta is going straight up.
Yes.
And I have Fn sine theta. Oh, actually, wait, I have my ramp going the other way. So Fn sine theta is in the same direction as cosine theta.
Yep. That's exactly it. And so we have these components right here. All right. Now, who applied Newton to this? You got it? Go.
Friction cosine theta plus Fn sine theta equals NA, and that would be the sum of forces in the x or centripetal direction because of the project. And then sum of forces in the y direction is Fn cosine theta minus mg, which equals 0, and Fn cosine theta equals mg, and that's Newton's first law.
I'm good with everything here except I count 1, 2, 3, 4 terms, but 1, 2, 3, 4, 5 arrows. We're missing one force.
Oh, I said F. Wait.
Oh, did you say F sine theta? Did you have it F sine theta?
Fn sine theta? Yeah. F.
So, in the vertical direction, we've got Fn cosine theta pushing up.
Mm-hmm.
And we have mg pulling down.
Right.
And we also have friction sine theta pulling down.
I thought friction sine theta would be in the x direction. My diagram
So,
looks a little different.
do you have F sine theta vertically?
Yeah, okay. It's really messy, I'm sorry.
It's okay.
It's opposite if you have the ramp going this way versus that way.
I think, is this your FS sine theta down, or is it across? It's hard
It's
to see.
across, I think.
Okay, so I think your components are backwards for the friction.
Okay.
Yeah. And the reason that you can tell that they're backwards, if I look at the original force vectors, friction is perpendicular to the normal force, and because it is perpendicular to the normal force, the sine and cosine components in the various directions will definitely be opposite from one another.
Okay.
So here comes my angle theta. If I do a parallel line cut by a transversal, that's my angle theta right there. That means that's 90 minus, and that's theta again. So the vertical component of Fn is adjacent, but the horizontal component of friction is adjacent.
Okay.
Just as a rule of thumb, when two forces are perpendicular to one another, their sine and cosine components will be opposites.
Okay.
Does that make sense?
I'm just trying to take it all in.
Yes, sir.
So you have theta labeled in blue there,
Yes.
but you also have theta labeled in the triangle.
Yes.
Is that the same angle?
It is the same angle. And the reason for it is what I'm doing is drawing an auxiliary segment, like you learned in geometry, and I'm observing that these are parallel lines here, cut by transversal. So theta's here, and that's 90 minus theta, and therefore that's theta.
So it would be the same angle, but in a different direction? Okay.
Oh, no, I think I got it. I just didn't write it down.
Oh, okay, great. So you had everything except just in the Newton's laws. So how many of you got to this point? Good. All right. Anybody confused? Got questions? Questions? Okay. So now what is necessary is for us to do a little bit of solving. I think we're all comfortable with writing the acceleration as v squared over r. And if we take stock, we've got one variable, two variables, and three variables is our Vmax.
This is the, oh, okay, this is the next one. What does that say behind cosine theta?
Where? F. Yeah, friction. That handwriting. So since we have three variables but only two equations so far, we need one additional relation. What is that additional relation? We've done this a lot of times.
Is it like friction is less than or equal to coefficient of second?
That's it. That's exactly right. And in particular, since we're at the max, we can actually set them equal. We're at the break-free one. So I'm going to replace friction with what it is in both equations. Let me label my equations as 1 and 2 so we don't get lost. And equation number 1, when I replace friction with mu times the normal, gives me mu times Fn times cosine theta plus Fn sine theta is equal to mv squared Vmax squared. And equation number 2 becomes u times Fn times cosine, no, just Fn times cosine theta. There we go. Minus mu times Fn sine theta. And I'm going to add mg to both sides in order to line my variables up. So in terms of good algebra strategy, it is a good idea to get your variables all lined up here. Does that make sense? Now, I'm going to help out a little bit with the algebra because you may or may not have thought of this. What I really want to do is I really want to get Fn, I want to eliminate Fn from the picture. And the reason I want to do that is I'm trying to find Vmax. trying to find Vmax in terms of everything else. So on Fn must go. Marvin K. Mooney, will you please go now? Anybody read that book? It's Dr. Seuss. Marvin K. Mooney, will you please go now?
Okay, what's it called?
No, it's the answer.
Marvin K. Mooney, please go. It's about this Marvin K. Mooney person.
I read a lot about this.
All right.
I'm kind of ashamed.
So what I observe is that every single term here, 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 all have Fn. And that suggests to me that I could get rid of Fn if I divide one equation by the other. It seems so obvious when I say it like that, right? But somehow they don't teach this very much in algebra. Not only can we add and subtract equations, we can multiply and divide them if we need to. And I want to. I'm going to divide. And when I divide, what I get is that I get this right here. And that's kind of nice. Notice that I appealed to a common slogan that you, if you're my calc student, you know I say it all the time. What did I do here to here? Factor, because factoring is my friend. Absolutely. Does anybody else see any other things that can? I saw some motions over there. You see something else that can be simplified?
Can you divide? Oh, you can't divide.
No, because mu is not a common factor. Good. Good catch. How about the masses? The masses cancel out. Yeah. And when I simplify over here, then I simply get Vmax squared over Rg. And over here, honestly, it's kind of a mess. And there it is. Now, is this my answer? Well, unfortunately, almost. And the reason for the almost is that I have not yet arrived at a Vmax in terms of V0. I have a Vmax in terms of theta. So somehow I'm going to have to come back and replace that. We're going to tackle that tomorrow. But here's your job for tonight. What I would like for you to do for tonight is to take the Vmin situation, three-body diagram, Newton's laws, and just as we did today, find Vmin squared in terms of theta, just like we did for Vmax. You can go back and look at the expression that we have right here. Yeah,
So those two equations, that was sum of forcing the x and sum of forcing the y.
exactly.
So it wasn't Vmin and Vmax.
No, it's just for Vmax. For the Vmin situation, if you think about it, your frictional force is going to be going in a different direction. Because now your car is not trying to escape off the ramp. Now it's threatening to slide down the ramp. And that really does happen, by the way. My wife was parked in the parking lot for her work on a day that was icy, and she came out to find that her car had slid sideways down the hill into the next car. That was parked right next to her. No damage done, because it all happened at like half a mile an hour. But still. Okay, is everybody clear? And especially those of you who did not do it last night, make sure that you do it tonight, because there's not a whole lot of value in just you watching me do it. You know what I'm saying? Your brain has to engage with it. Make sense? Good. All right. Let's review work energy. what we've done over the last couple of days is to define two quantities that turn out to be equal to one another. The work done by a force. And the picture that we have is that we have a force that is being applied to an object as it slides or moves a distance d. And when a force is applied over a distance, it does work. And the formula for that work is, everybody? Fd times the cosine of the angle between. And the way we measure that angle between is strictly between the two vectors, bless you, and it has no relationship to our coordinate system. It is a coordinate-free representation, which we love. We also defined a second quantity called kinetic energy. Kinetic energy 1/2 mv squared. And what we showed yesterday is that when an object does work, when a force does work on an object, the result of that work is to change the kinetic energy of the object. And this was our famous work energy theorem, one of the most widely used theorems in physics. Even more so than the equations of motion that you know and love so well. The work energy theorem is that the amount of work done on an object is equal to its change in kinetic energy. Another way to rewrite this algebraically is to add k0 to both sides and say that when a work process happens, the final kinetic energy of the object at the end of that work process is equal to the initial amount plus the amount of work done. Yes.
Is kinetic energy expressed in joules, or is that
Yes,
work?
it is. So if you take a look at the units for kinetic energy, of course the units for 1/2 are just 1/2, so we'll leave them off. And the units for speed are meters per second. And when I square those, I get those famous units that we have seen, kilogram meters squared per second squared, which is the same as a Newton times a meter, which is the same as a joule.
What about work?
Mm-hmm.
Work. So work's also expressed in joules?
Newton's meters.
Got
Yep.
it.
And it has to be since they are equal
Yeah.
quantities. Yep. So a big analogy or a metaphor for energy that we want to think about is that energy is very much like money. The way in which you change the amount of money in your pocket is to receive or take away money from your pocket by receiving payment or paying something. And so work is like a payment of money, a transfer of money. Money changes hands. Energy changes hands when work is done. And the money in your pocket is essentially the kinetic energy that you have. When you have zero kinetic energy, what is your speed?
0.
0, you're stopped. When you have zero money in your pocket, you're broke. So having zero kinetic energy is the particle's version of being broke. At that point, you're stopped. You have zero energy. Okay? So, that was our lesson so far. What I'd like to do now is I'd like to turn our attention to 7:12 in terms of computation of work, and then we'll try to do a work energy theorem problem as time permits. In number 7, we have a situation in which a kind of a seesaw, it's really called a fulcrum, is placed on a rock. There we go. And they express it like this. we have a fulcrum right here, and I'm going to represent that fulcrum with just an arrow. That's not a vector. All I'm trying to do is to give this fulcrum a sharp point to rotate around, okay? And we're going to place a rock right here of mass m. We're going to put a force on the fulcrum so as to cause the rock to move. Now, if the rock moves with constant acceleration, then my force is going to have to, if my rock moves with constant speed, then my acceleration will be 0, and that means that the rock is going to push back on the fulcrum with a force of mg. But interestingly, the force F that is needed to lift this rock is not mg. And the reason why not is that this force is going to be contributing energy to the rock. At the same time, gravity is going to be taking energy away from the rock. And the amount of energy that the rock has at the end will be the same as the amount that it has at the beginning, because of the contribution of all the forces there. So if I consider that the work done by this force as it goes over this distance d1, and let me call this force F2 right here.
Isn't energy going down?
In order to lift the rock, the fulcrum is going to need to push upwards with a force of mg at that point, right? And as a result, my seesaw is going to go down, fulcrum, and we're going to go a distance d2. So everybody should be able to see that d1 is a whole lot bigger than d2 for the simple reason that we've chosen our fulcrum point to be shorter, so that it is towards the shorter end, towards the rock end, like that. Everybody with me? And so what I claim is that because the rock starts with 0 energy, it's not moving, and it ends up with 0 energy, also not moving, that the total amount of work done by force F1 has to cancel out the total amount of work done by force F2. So we can express it like this. Just like that. And because of that, that immediately gives us a relationship between the two. Which is an inverse relationship. The longer d1 is, the smaller f1 is. And the more powerful f2 is, the shorter d2 will be. In other words, what I'm doing with my fulcrum is I'm conserving energy, but I am trading force for distance. The person lifting the rock has to push a longer distance d1, but as a trade-off, he gets to use a smaller force. We use this idea in robotics all the time. And we use this idea basically to enable us to exert small forces on objects over longer distances so that we can get large forces on the objects that we want to propel. Does that make sense? So this is one of 6 simple machines. And it's called a fulcrum. And what it does is to trade force for distance so that I can use a small force over a long distance instead of a large force over a small distance. Can anybody tell me any other simple machines that do that same thing? A pole, a block and tackle can be one of those. Yes, exactly. What else?
A spring.
A spring? No. For a spring, you pretty much have to push as hard as you're going to you pushed on,
I
yeah.
just have a question.
Yeah.
So would the opposite of this be like pushing down really hard, so the rock, like a lot of, I'm confused, so it's saying less force over a longer distance?
Yeah.
So if you were to like push down really hard and the rock went up on its own, would that be large force, smaller distance?
You ever been to a park with a small child?
Yes.
You ever been on the seesaw?
Yeah.
Okay. Which one of you has to sit closer to make it work?
Closer to heavier.
The heavier person has to sit closer. That's it.
Distance is like the length of the board. So if the board, wherever,
No, the distance is the vertical. No.
yeah,
Ah.
so if it's longer, the distance is greater, so then less force is required.
So L1 and D1 are not the same number, but they're also proportional. Why? What famous shape do I have here? I've got, not rectangles, but I've got similar triangles. That's right. These two angles are congruent because they're vertical angles, and these two angles are congruent because parallel lines go by a
Wait,
transversal line.
so if you, can I, one second.
Yeah, but let me just write this in right here.
So like if you push from here,
Mhm.
so if this was the board, you
Yep.
push from here, the rock is here. that
Then
would
you would
be,
have to
like,
push
the
really
opposite.
hard. Yes.
That would- okay.
That would be working against yourself.
Okay.
Yeah. You would only do that if you had overwhelming force and you wanted to really launch the heck out of that rock.
Yeah.
Yeah.
Alright.
Yes. Does this make sense to everybody? Okay. Let's talk number 12. In number 12, what we have is a force that is given to us in terms of a graph. Can you hold the graph up so I can copy it? Wrong graph. Hey, you, go away. There. That's the graph. Does it ever take you a really long time to come to a realization sometimes? I spent years with just that one graph right there before I said to myself, I need to have another graph that has the axes on it. You'd think that would get there faster.
Is this both in Moissanite somewhere?
It is. And we have, I'm just going to mark this place here. 3, 7, 10, 11 and a half. It's probably, that's probably not. Okay, and then the force is given to us like this, here, down to 200, over, and back up. Wow. So the force is given to us in a graphical form like this. And so now they ask the question, how much work is done by that force as the object moves from x equals 0 to various points along? And I don't remember the particular points. So I'm going to make up a couple of points here. Let's say work done as object moves from x equals 0 to x equals 7. And we'll go to x equals 10, and then we'll go all the way to x equals 15. Okay? Does everybody understand the setup for the question? Okay. Here is the slight difficulty with that question. Work is equal to force times distance, right? But my force is changing. Oh no! Oh, wait a second, I've seen this before. We dealt with changing accelerations, didn't we? Changing velocities. And the way we handled that was by appealing to the idea of area. Since work is force times distance, if I take this entire distance from 0 to 7 and I split it up into little teeny tiny distances, then for each one of these little teeny tiny distances, my force is essentially constant. So the area that I have under the curve for that little teeny tiny distance, pretending that the force at this point is the height of the entire thing, pretending, represents a very small amount of energy, maybe millijoules, that is added during that little tiny displacement. And if I go through and do rectangles for the whole thing, like so, that cover exactly my curve, like this, then the area underneath all of those rectangles added up will be the entire amount of work done. In other words, work equals area under the force curve. This is not a new formula. This is simply an extension of our FD cosine theta formula to the situation where my force is changing. When you get to calculus, you'll learn a slightly different way of expressing exactly the same thing, and we'll be able to do it very powerfully in a lot of different ways. That's coming in January for you guys. Okay, so in other words, the big principle is that work equals area under the curve f of x. So that makes life easy. All I have to do to go from 0 to 7 is to find all of this area. And this is a simple shape. It's a trapezoidal shape with two parallel bases, here and here. And the area of the trapezoid is the average of the bases times the height. And the average of these two bases is the average of 7. 7 meters, in fact. And this would be 4 meters. Times the height is 400 newtons. Notice when I use both the width and the height, I measure that according to the meaning of each square. I don't count squares. I go to the actual numbers. So that what I get is 200 times 11, or 200 and 2,200, excuse me, Newton meters worth of work done for that. Does that make sense to everybody? Yeah, that's exactly right. And if it's some weird funky shape, I'll force it to be a simple shape and treat that as an approximation.
Oh, okay, I see what you're saying.
So if my curve looked like this,
So you would just have to draw.
I would do a triangle and say it's a little bigger than my triangle. I do simple shapes only for my areas until you give me calculus tools, and then I can do any shape you want as long as I know the equation. True story. So what if I go from 0 to 10? Well, the only thing that changes as I go from 0 to 10 is that I'm going to now add on additional area. I can handle this in one of two ways. I can recompute the whole thing as one big trapezoid, or I can take the area that I already got from 0 to 7 and add additionally the area from 7 to 10, which is a triangle. I'm going to do that. So from 0 to 10, this is the language that we want to use to describe our work. I'm going to describe it as the area from 0 to 10. Then I'm going to say that that's equal to what I got from 0 to 7, 2,200 joules, plus 1/2 of base times height, 1/2 of 400 times 3, which is equal to another 600 joules. And so the idea is that this force just gave me a payment of 600 joules, increasing the energy of my object. Now, when we get over into x equals 10 through x equals 15, look at that, my force is now negative. What does that mean? It means my force is pointing in the opposite direction that it was before. You can imagine this. Maybe somebody is pushing a cart, and they push it, and by the time they get to x equals 10, they realize, hey, wait, this is going too fast, and they start pulling back on it. And now they're exerting a force in the opposite direction. See what I'm saying? At that point, the work that is done is going to be negative because the force is pointing opposite to the direction of travel. That's our special case number 3 we talked about. So that means I'm going to count all of this area in here as negative. What is that area? Well, it's from 10 to 15, and this is apparently 2 across. So I have the average of, hang on, 2 plus 5 times, watch how I handle this. I'm going to call that negative 200 newtons. And when I do, naturally, I get negative 700 joules. That subtracts away from the network. Was that helpful?
Yes.
Good. Tomorrow we'll start conserving energy.